Hello? Oops, didn't want that to happen. Well, this is not a good idea. Yeah. How we all doing today? Good, good, good. How's that homework assignment treating you? Ooh, what pray tell are you? Useless, I think. Damn it. Okay, useless. Figured so much. Your volume is very low compared to the music. Of my voice? I was talking quietly. I think might have been the issue too. Yeah, no, thanks for pointing that out. I was doing some recording for my cloud class and I'm a little worried the volume's too low for that one. It's the whole enunciating thing you have to do. Yeah, I was gonna say the music volume should be quite low, so I have it set pretty low. Okay. Nothing useful. Okay, I like that one. Make this work for me. Useless. Okay. I had a delightful run queued up for you all earlier, and then I wasn't paying attention, and I died halfway through the game. Instead, we get boring 3 damage Isaac. Which is fine. This is not the hallmark of the class anyway. Oh god, that was bad. Let's go that way. Stay over there. Appreciate it. Thank you. Car. 4 minutes until class. These guys are annoying to lost. Money. Tempting. Somebody rendered this game out in like a real visual, and it was absolutely disgusting. It makes you realize the themes in this game, once you take away the cartoony exterior, kinda gross. Oh, that is right. I need to make sure this is visible. Yes, there's a chance we do some whiteboarding today. And that's definitely not a whiteboard precariously balanced on an IKEA table. Alright, 2 minutes till class. Who else is here? So how's everybody doing with that homework assignment we started last week? Any major problems with it? Concerns? Oh shoot. Yeah, let's see, so I gave you got a couple of questions. Questions on the lab or just on stuff in general? I guess, yes, I've got a couple minutes. Sure. That's not where I want to be. Assignments. March 19th. So that should be Friday. Okay. And let's do one more room and then we'll call it good for now. Oh, it's fun when runs start to take off. What are you? I don't need to be larger. All right, so while we get set up for class, basically where we are currently at is we are on the last real straight up basic WebGL lecture starting today. And that will take probably 1 to 2 classes. I'm going to guess at least 2. There's a crap ton of slides to get through. But we're going to be talking about model building. We are going to be talking about setting the camera. And then, since we are after the midterm, we're going to pivot towards Blender, we're going to pivot towards Unity, and basically we're going to look at other technologies because for me, let's fix this here. Okay. I like you all to get as much experience as possible in other frameworks. I know WebGL hasn't been the most exciting or the most fun, at least from quickly prototyping and releasing things, but you do get that appreciation for what's going on under the hood. And everything you're learning in this, um, you know, from up until the midterm and, these next couple lectures, it's all transferable to Unity or Unreal or Godot or whatever you're going to take it to. All of these transforms that we're going to be talking about and that we have been talking about, they're the same, right? If we figure out, quaternions, if we figure out angles of rotation, transformation matrices, these all exist everywhere. It's not a WebGL with this particular guy's library kind of a thing. So hopefully that's going to be helpful for you. If I remember later on, I've got a nifty demo I can show you when we get to Unity. Basically what I had, and I actually made a little like welcome video to GVSU when they hired me in last year because they were looking for professors to do social media stuff. So I grabbed one of my Raspberry Pis. This is a phone, but I have a Sense hat that goes on top of it, and it's got a bunch of sensors. It's made for hobbyists. They've been sending them up to the space station, I think. I've seen a couple of projects like that, but they have a bunch of GPS and gyro and types of sensors on there. And I had this Raspberry Pi. I could kind of rotate it in space, and that would translate over to a Unity project. Basically, the Pi was transmitting its telemetry to Unity. Unity was reading that in and translating it on the screen, and that was kind of fun. So I'll have to see if I can dig that out for all of you. Turns out that Unity is a pain in the butt to do networking with, at least in its current form. I don't know if any of you have experience with that at all, but at least when I was playing with it last summer, they had stripped out their networking components that were commonly used and they were planning on upgrading them. But it was kind of in this weird in-between space where there's nothing perfect. So I ended up using raw C# sockets and it was horrible. I actually had to get code off of a German forum, translate the comments, and figure out exactly what they were doing with it because it was not pleasant. But we'll get to that. I'll try to get that up and running for you. So we have Lab Due Friday. Don't forget about that if you just popped in. I wanted to show you one other thing too before we get into models. So I know I keep talking about P5 and I'm excited about it because this is a new thing for me. I know a lot of you have seen it before, but I've been kind of checking out some of this generative art type stuff that you can do with it. And here's something I came across on Reddit. So this is in processing sub, but somebody translated this to P5. And it's really simple. Real programming is drawing. Absolutely. That's how it works. But basically, I just kind of grabbed the code from that P5 post and I dropped it into the editor here. And I mean, 28 to so 6 lines of code in the draw function and just figuring out a sine wave and then just kind of recursively, well, not recursively, but there's a for loop here, just iterating through various sine invocations, and you can generate some pretty cool stuff in here. And I've got a separate project that I'm kind of working on in P5 just to kind of play around with it. Kind of the point I was making with this is that I could very easily see this translate over to WebGL if you wanted to do it in something a little bit more performance than P5. So one of the things I will mention, I've been playing with this type of stuff as kind of a lark, but it takes forever to render. It is poorly optimized. It's not intended for what we're doing with WebGL. Right, this thing can't really handle a ton of objects or a ton of particles. It's all CPU bound. But I mean, what's going on here? We have some basic sine calls. We have a for loop, and we are just randomly generating some points. That's all this particular thing is here. Why is this black? I just take one out. It takes about a solid minute to render if you're doing the default code. And here's, I took out a order of magnitude, and you lose some fidelity there. But it's kind of fun. And I know I popped the link in our, come on, there we go, in our channel here. What are all these mentions going on? Ooh, there's stuff happening in Discord. All right, so just some fun stuff to check out. Bot spam, bad bots. I updated this. Grr. Sorry. Me6, you are not saving. Okay. I so updated this. Ah. Oh well. Welcome to the software engineers if you're in here. I literally did that an hour ago. Oh well. So, something fun to play with if you're looking for term project ideas. And one of the things I also wanted to mention as I was kind of bringing this up, again, just because it's a little bit of a fun thing for me to be playing with and to show what's possible. Your next assignment, I'm going to ask you to make some progress with your term projects. So I'll probably have a short, probably not a full assignment, but a short little survey, like what are a couple of things you need to do to get started with your projects? Because again, you gave me some ideas, and more or less outside of some scoping, they were all pretty good. So what's going to kick off working on it? You know, outside of me telling you, hey, it's time to work on it, I suppose. But, you know, like what are some things you have to do to get going? You know, if you're doing it in Unity and you've never touched Unity, maybe you need to walk through a tutorial video if you want to get up and running, or work on a design document for what your data structures are going to look like. Are you doing a 2D thing or a 3D thing? Just those kinds of ideas to get you thinking at least. All right, but that's forthcoming. I'm not going to make you do that before the current assignments do, because I know not everybody has it done. So, without further ado, let's talk models. This is different. Okay, we have a new Google Slides interface. Is somebody watching my videos and seeing me frustrated at the little bar that keeps popping up? All right, so where we ended up last time, well, we didn't really start here last time, but we have been talking about transforms. We've been talking about, you know, building up matrices, working on our matrix math, offloading all that hard work to the GPU and our library. Now let's start building up models. And once we get through building up models, we'll start talking camera and perspective. And the kind of key takeaway here is that part one is basically just going to be data structures. And it's really mostly common sense, I would think. You know, if I'm going to say that with a massive caveat, like if we haven't even considered it and we haven't gotten that deep, it's not common sense. But once we start progressing, it's going to be very clear we need some way to manage these things, because we're not going to be doing triangles forever. They're simple triangles. We're going to need to do more complicated things. All right, so when I talk models, this is what I'm talking about. All right, we're building up a mesh around some kind of a 3D model, or even a 2D model, just kind of depends what we're showing. The second part, which I'm going to guess is mostly going to be next time, we're going to be talking about the different types of perspective, meaning how we view objects. So if any of you have ever taken a CAD course or a drafting course, you're probably going to feel right at home there, because we'll be talking about things like isometric views, we'll talk about parallel views, we'll talk about perspective, we'll talk about axonographic views, and all that fun stuff. And kind of the fun thing is that it's really trivial for WebGL to handle that. To give you a spoiler there, going from isometric to perspective, or going from, an oblique projection to a 3-point axonographic projection is just a different matrix that we feed into our pipeline. That's it. Again, we're just basically filling in holes in these matrices that we are going to multiply by. And there's a massive amount of math that went into figuring these out, but they're all standard now, which is nice for us. So let's start with modeling. Now, my perennial joke for modeling, don't search Google Images for models because you don't actually get what you think you're going to be getting for your class. It only took me one live search in class to realize that, but I'm sure I've made that joke already, so we won't dwell on that one. But what do we need to model things? We need something to actually store data for everything that we're going to be managing with this model. What have we been dealing with so far in terms of drawing? Vertices and colors, right? That's pretty much all we've touched. Everything we have set has been basically absolutely positioned. So that's not always a nice thing. Let's give an example from the web programming domain. I know some of you have made websites before. You probably even have touched cascading style sheets. If you absolutely position something, so I absolutely position something in space. Let's say I've got, I'm going to put link right in the center of my board. If I set his position to be absolute, he is 100 pixels to the x-axis, 100 pixels down in the y-axis. If my display changes, he's going to move up here. Like I move it big, I make it bigger. And if I make it smaller, he's going to be clipped off of it. So the issue with, and kind of why I'm bringing this up, is that we have the same notion in graphics. If we are setting pixel positions, it's going to be better to kind of abstract it out just a little bit. And we can't really get away from setting them absolutely. We need to set this pixel position at, 0, 0, 0, or 1, 1.253, wherever we're putting it. But if we want to work with that vertex later on, we don't want to search for it, if that makes sense. So let's talk about what a mesh is now. And I've got a formal definition for you here on the slide. I'm sure you've read it already if you are paying attention to what is on the screen. But a mesh is basically just a collection of polygons. So these guys here, these are all meshes, right? So this is a mesh of these kind of rectangular polygons. Now, if we're drawing this in WebGL, each polygon here is a set of triangles, right? Here we have one triangle here, one triangle here. Can I get my laser pointer back with this new interface? Oh. Ooh, we have hotkeys. No, we don't have hotkeys. Hitting L doesn't make it go away. All right, got to work on your interface, Google. So we have one polygon here, right? We can bisect it. Now it's two triangles. We can represent this thing. Everything here is a set of polygons. This is also a set of polygons, right? So turn off laser pointer. We just have a ton of polygons so that it looks like a smooth surface, right? In this particular figure here, we've added on some wireframe lines so that you can actually see what the polygons are, and we can see the density of them is a lot more. What does this translate to you, the WebGL programmer? Well, this figure here is a heck of a lot easier on the processor to render than this one, because we probably have a quarter of the vertices to deal with. And again, think of this programmatically, not necessarily visually. Yes, this is what we want, but if our computers can't handle this because there's just too much going on, you have to cut corners and do something like this. Reduce the vertex count, reduce the polygon count. These are things, if you have dealt with a modeling program before, these are attributes that you can set. Basically, what is the fidelity of your model? And you can get away with some nice little cheats too, right? If you want to have a nice looking graphics environment, we can take the Legend of Zelda game where he was on the boat the entire time. I just think of it as Toon Link now, but it's I swear to God, my short-term memories just disappeared on me. Zelda boat. Not Breath of the Wild. Oh, come on. Wind Waker. There we go. Thank you, Nikki. Yeah. I did know that. I have played it. It was a great game. Mindless boating, regardless. It's beautiful. People hated it at the time when it came out because it was so cartoony, but that kind of perspective and that kind of visual holds up over time, whereas something photorealistic tends to kind of go away and as we get better and better. So there could be something to be said for having a polygon count that's lower, as long as it's nice and stylistic. Right, so we have a mesh. Mesh is going to be made up of a bunch of triangles. Now, let's take it to a bit of a more detailed view. So here we have a polygon of some kind, right? So this is a mesh. The V's are vertices, the E's are edges, edges connect vertices. These are all going to become, apparent why we're using these terms later on, because there are actually rules in what order we draw things, too. So we have zero notion of Z in this particular figure, right? This appears to be a 2D object. There's nothing stopping vertex 7 here from being, pulled closer to the camera in this thing being kind of a pyramidal type of shape. We don't have that information here. But what we do is we have a bunch of things to keep track of. We have 8 nodes, so the little green dots are nodes. We have 12 edges. These are the things connecting them. The vertices, or nodes, each has position, x, y, and z. And if we are in 2D world, obviously it's just x and y, right? And we leave z off. But some things to note here. We have 5 interior polygons with this object. So we have 1, 2, 3, 4, 5. And then we have one greater polygon that we can make out of those shared polygons, right? Another term in here, we have 6 shared edges or 6 interior edges. And this will become important as well when we start trying to make a data structure to hold this thing. Okay, so we have 1, 2, 3, 4, 5, 6. So basically all the lines inside of our object are interior or shared. This is kind of where objects being convex are important, so that we can basically use all your various algorithms for triangularizing or for basically generating a mesh. A lot of them require convexity. Otherwise, we have to split the object up if we remember that. So, basic ideas that we're going to be working with here. So, almost lost my T. That could have been bad. Most simplistic representation we can do is let's push down our vertices. So here I'm pushing down a triangle. Okay, so this is everything that you have been doing so far in every lab, every homework. Let's create a list of vertices. Let's push down a vec3 for every vertex, or vec2 if we're doing 2D stuff. And that is our polygon that we're going to draw, right? If we're going to go ahead and represent this thing, I would have to do that for every single node. And I would have to make sure that I do it in the exact correct order. Otherwise, this is not going to look right. Those of you that were playing around with the, when I gave you the exam question for the draw the pentagon, and then I said draw a hexagon on the exam because it's just one extra vertex to deal with. You had to push them down all in the correct order, very specifically, otherwise it didn't work, right? You'd have missing chunks of your figure, or you're going to have something very spiky and weird looking. So there's a lot of very precise things that have to happen in this particular fashion. This is also very, very inefficient, meaning that if I want to say move, sorry, I should have stayed here. Let's say I want to move V7. And I want to move it over here, and I want to push it away from the camera so that our, pyramid type thing is now an upside down pyramid. Maybe we're modeling the Louvre or something like that. I've got to search for that thing, or I have to keep track of what every single vertex is in some fashion. Okay, 7 vertices, not a big deal, right? But our polygon counts are not always 6 faces. or 6 polygons. We're getting in the millions of polygons to deal with a real model. So if I want to search for one of them, or, a subset of them, I'm going to have a very bad search algorithm that I'm going to have to implement to find things. So what do we do? Any guesses on what we can do to solve this problem? Now, hopefully the idea makes sense. How do we resolve the search? Any thoughts? Well, since I'm guessing there are no good guesses here, this is not a new problem for you as computer scientists, I hope. If we want to avoid searching for a particular value every time, what do? Let's add an extra layer to provide, say, a lookup table, right? What we can do is we can represent each vertex, still like this, but we can represent it as a list of edges, or as a list of figures, or a list of polygons, and we can basically add on layers of complexity. So if I want to shift an edge, what is an edge? It's just a line with 2 points. I could say its starting endpoint and its ending endpoint. I could pretty easily look those up, but I don't have to search for, if it's at 4, 3, 2. Basically, we're just adding on extra variables here, extra objects. And the kind of idea is it will basically create pointers or lookup tables. To skip ahead a second here. One other thing we have to do when we're dealing with polygons is we have to define them in the correct order, and that's one thing that I mentioned. So if we have this figure here, and I'm going to pretend there's a triangle right here, okay? And let me actually dip out of full screen mode and go into edit mode here. I'm going to make this just a little bit bigger, and hopefully I can undo this without breaking anything. There we go. Now I don't have to draw on the board. So I'm going to say that I have a triangle right here. All right, so I'm going to add an extra line because we're skipping. No, I'm going to add an extra line, please. There we go. Here. Let's make this a bit bigger so that we can actually see it. Because I'm dealing with V1, V6, V7 in this particular instance, okay? So we're going to pretend like the rest of this object doesn't exist for now. The order is important on how we define these things, and you've seen that kind of inadvertently. But if I say something is V1, V6, V7, and then I say it's defined as V6, V7, V1, or V1, V6, V7, these are all the same thing. Okay, so if we're going in the correct rotational order, meaning that we always define them kind of in the same rotational pattern, it's the same type of thing for WebGL. It's when we reverse that it becomes an issue. So if I called this triangle V1, V7, V6, so I kind of went this way, that would be problematic. Does that idea make sense to you all? So the reason why this is problematic here, let me excuse me, let me undo this here. There we go. Okay, so basically what we've got going on is that WebGL, whether we like it or not, is going to try to help us out with depth and with culling. And I need my notes over here. Basically what's going on is we're going to, based on the order, WebGL is going to understand what is the front and what is the back of an object. All right, so if I am going to define this thing as v1, v7, v6, I'm going to basically define the order as going kind of counterclockwise. And if we apply what is, another version of our right-hand rule, which we mentioned multiple times, we've used it for various things. Before we used it for our axes and our frames, right? But here, we're going to use it in more like an electrical engineering, mechanical engineering fashion, where we're going to follow the rotation of our fingers. And I'm trying to see if I'm doing this right on camera. If we are going this way, the front is the direction of your thumb. So if you look at this figure here, if we define this particular square as vertex 0, 3, 2, 1, this is the front. The back would be the opposite direction. So if we define this particular triangle here as v1, v7, v6, this top is, or this point is going to be the top. The other side of that would be the back. And this is, again, because we have the notion of depth in WebGL. And we're not going to display the backside. So that's kind of the notion here. And when we start building up meshes, it's going to be important in what order we put things. Because let me go back to the very front here. If we are defining a person's face, and I define, obviously we'd have an algorithm defining this, right? But if I'm defining this polygon here, and on the front of it's his texture, maybe it's my, blotchy skin that we've got going on here. If I define this in reverse order, it's just going to show the back of whatever that texture is. And maybe it's mirrored or flipped, just kind of depends on how we've applied it. But we might be getting the wrong thing here if we define vertices in the wrong order. So just kind of the key takeaway here is just make sure that you're very careful with how you define ordering of your vertices. And for us, thus far, it's been straightforward. We just kind of push them down into our vertex list, and that's the order, right? Again, that's getting translated into that one-dimensional buffer. And it's still going to be the same no matter how much extra fluff we add on top. It's still getting flattened out, but we're making life easier for us from the application perspective. Okay, so put your things in the right order. And if you are lost in what the order is, take your right hand, follow the correct, so if you do a counterclockwise motion, that direction your thumb goes is where the outward face is going to be, or the outward pointing normal, as the slide says. Basically, the normal is just a perpendicular line off of the polygon's face. Okay, all that was just to tell you put things in the right order, which intuitively should make sense, but becomes important in meshes. Now, we need to figure out a little bit of separation of concerns here. Everything we have been talking about thus far has only focused on one aspect, and that is the geometry. So the geometry, let me take the example off first here, is the exact vertex positions. Okay, so if I draw a triangle, let's use this board since otherwise I'm not going to use it today probably. I draw a triangle, so we have vertex 1, vertex 2, vertex 3. My normal's coming out because I've drew them in this particular fashion. The geometry is the vertex positions, right? So this is going to be 0, comma 1, 1, comma negative 1, negative 1, comma negative 1, right? Day 1 triangle. This is our geometry. If we want to be smart about this, we'll separate this out into a topology. So we're basically adding another data structure to separate this out. And what this is going to get us is that I can say, do something like this. All right, so let me now get another color because I have this available to me. I'm going to draw another line or another vertex. I'm going to move this guy over here. This is now, I don't know, 0 or negative 0.5, comma 0. If I were to do this as you all did before, either I'm sliding a theta variable in and I'm kind of rotating things around, right? We did that. Or you just update that position. We didn't do that very intelligently. If I track this vertex as a topology member, meaning that I define a data structure that tells me what a triangle is, I can just say pick vertex 1 and shift it. And by doing this, we could extrapolate that every single triangle in our object we could deform. Instead of going through and figuring out, okay, what's the third vertex of every object, right? So if we step through our array buffer, okay, from buffer point 20 to 500 are our triangle vertices for the face of Kirby, I guess. Every first vertex needs to shift, or all the other ones have to shift because we're deforming this thing. Basically, we're adding on a lookup table is all I'm kind of getting at here. So kind of the other example, if that didn't really hold with you, let's say that we're defining a line loop, which we could do with a triangle. But again, a line loop is basically we start here, we're going to end here. So I could have a vertex up here, a vertex over here, a vertex over here, realizing that you probably could have drawn your polygons this way too. And then I'm going to close off the line loop. If I move this vertex, the topology is going to be the same, but the geometry changes. So how do we separate this out? Well, let's put our geometry into an array, which we have been doing, right? So this is our vertex list, and that thing that we call flattened vertices, that's what this is. But we're going to add some pointers. So if we have a particular polygon, say triangle 1, triangle 2, triangle 3, P1, P2, P3, these are going to point towards a list of vertices. Polygon 2, point towards a list of vertices. And then these point to the exact vertex position. Okay, so if I want to dink around with, say, polygon 500, I just index into this object, and it might be a dictionary, it might be a list, whatever tickles your fancy for your particular language. Again, this is not a JavaScript specific thing. This is any graphics language. I'm just going to interact with this object, and by notion of having these vertices defined as comprising that object, I'm going to indirectly interact with them. And yes, it's adding a layer of complexity, but the net benefit is so much greater than not doing this. If we're doing it for one triangle, it doesn't make sense. Okay, I mean, that's extra effort. It's when we start building up a lot more complicated meshes and polygons that this really starts to really take off for us. So we're going to separate things out. And the nice thing too, this is a preview for several slides down, we actually have other WebGL calls we can make. We don't just have to use draw arrays. We can draw based on indices, not strictly vertex positions. There's a function we'll be looking at for that as well. Performance, I think as far as I'm aware, can be negligible based on which call you use as well. Alrighty, so let's say that you're okay with this idea of adding in a list, and I'll show you an example in a few as well, because the GitHub repository website has examples of some of these various things. And actually, if you remember from the last time we looked at that color cube, that's exactly what we're doing here. We basically created an extra layer of indirection. So one issue we have to deal with in this particular instance, though, is if I'm going to be pushing down a bunch of triangles or a bunch of polygons that I'm going to represent, the edges that we share are going to be drawn more than once, which is a problem. Right, so if I have my figure here and now this looks like home plate, and I've got a vertex in the middle, so we're going to go ahead and make a fan out of this. Excuse me. Dusty in here, apparently. If I'm going to push every single one of these triangles onto a list, okay, and I'm going to add my layer of indirection. So I'm going to have a list of polygons. So I'm going to draw this triangle, then I'm going to draw this one, and then this one, and then this one, and then this one. You can see every time I draw a polygon, and hopefully is that visible to you all? If it's not, I can kind of bring it a little bit closer. I'm just looking at my camera and realizing how tiny it is. Here's my hand. Can you see the triangles? I guess I can color them in if you can't see it. Okay, I'll just do these three. Every time I draw a triangle, I'm going to redo the internal edge. All right, so if I were to draw this thing out, which is easier for you to see, I'm going to draw this triangle, and then I'm going to draw these triangles. These shared edges are going to be covered more than once, and you're going to get depending on how you have your WebGL set up, you might get like a doubling, or it's just going to be extra effort. It just kind of depends on what you're drawing. Like if you're doing a transparent line, you're probably going to start to see it get thicker and thicker, or darker and darker, I guess. But how do we get around this? Well, instead of storing polygons, let's store edges. And that way we only have to draw them once. The issue with this particular approach, though, is yes, we can now save our drawing effort, right? Instead of drawing, polygon, 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 we're just drawing, okay, draw this edge, draw this edge, draw this edge, draw this edge. What is an edge? It is just a list of two vertices. What's a vertex? X, Y, and Z, right? This is a different approach, I should mention from the last one. Create an edge list. Issue here, though, we don't have polygons. So I don't have a notion that this is a polygon. I don't know that this is a polygon. I don't know that this is a polygon. Because I'm just storing raw edge data. There's nothing in here telling me what belongs to what. All right, it's just going to draw lines in order, basically. But hopefully the idea of adding this layer of indirection is helpful for you all. All right, questions so far? Everybody buying this, hopefully. Please let me know if you're not, because if you are lost, this kind of everything builds on this. It's super dry in here. My throat's like already parched. All right, you go back here. Kirby, I'm sorry that you fell over. All right, well, so is there a correct direction in making your vertices to define a proper front? Yeah, so if we remember from when we first moved to 3D, basically WebGL is going to keep a notion of what is drawn first. So based on how you put vertices in is going to tell WebGL what is in the front and what is in the back. Plus we have the z-index information as well. So if you're doing like multiple polygons, we're going to be able to tell it, what is closer to the camera and what's farther away. And based on the ordering of the vertices, it's going to tell you what's the front face, what's the back face, things like that. Yeah, no, good question. So I realize that I have some discrepancy in between the slide and the actual definition here. So I've got cube.js open, and this is what I copy and pasted from something. I'm not sure where I copied this from, but it wasn't cube.js. But quad 0321, quad 1032. 1032, 0321. They are identical from the perspective of vertex ordering, because we're still counterclockwise, facing outwards. This next one up here, let's say 1265, where are we at there? 1265, 1265. Basically, if you look at the cube page, this was our example of indirect drawing. We didn't really go into too much detail on it, but this is a layer of basically help for you to start defining polygons. So we call this color cube function. Color cube calls the quad function. Quad defines the vertices in the order. All right, so on vertex 1, vertex 0, vertex 3, vertex 2. What's quad? Well, I'm going to take these vertices or sorry, these vertex indices is the correct way to say that. And then I'm just going to index into an array the vertices and vertex colors. So we kind of went over this a little bit last time in terms of, we could draw this thing as solid colors, or we could draw it as kind of that nice gradient, if you remember from last time. But what we're doing is we're going to say a quad is just a rectangular-ish object comprising two triangles. Based on these vertices that we push in, vertex 1 is going to be ABC, vertex 2 is ACD. So ABC, ACD. That would index into our vertex positions, and then we can play with them to our heart's content. Same with the colors. Now we can basically do whatever we want for coloring, but we now have tied our colors in with the secondary object as well. So basically every polygon has its own color based on how we colored the vertices. So hopefully makes sense. Again, it's a layer of indirection, but it helps us with building up these meshes. All right, and I guess one thing I should finish off here with, if I wanted to say work with this cube, we don't have any calls to say update the first corner of cube or of quad number 1, but I could very easily say store off an extra data structure that indexes into color cube here, and then based on how based on what is set at vertex 1, I can start moving things around, and then that would be tied to every single other quad here that deals with vertex 1. Right, I'm not drawing. I guess one other benefit here, I'm kind of talking in circles, but if I were to draw, say, this one quad here, let's go back to our picture. So I'm drawing this one first. Okay, so triangle, triangle 1, triangle 2. I have a lot less data that I have to send to the GPU as well. So well, I guess it's going to be the same, but I'm not redefining vertex positions, if that makes sense. So I'm not going to say push down this vertex here for the front face, and then I'm going to push it down again for this particular triangle, and then push it down again for this one that's kind of off to the side here. Yes, that is happening behind the scenes, but I don't have to manage that. My extra layer of indirection's handling that for us. But if you want some help with how to get started with that, check out the cube.js program that we've got. And I guess I can close my P5 editor. So that's going to be chapter 4 cube. That's this guy. Okay, so we have our cube. Now, one of the things that I mentioned earlier is that we have options for how we display things. We can display them by arrays, which is what we have done all the way up till this point. We called gl.drawArrays, and that's just going to draw whatever is in that buffer that we set. And again, that buffer being set is handled by our modules that we're importing. We can also call it by elements, which is helpful for you, the developer, because you're just dealing with like vertex indices. That list, that edge list that we looked at a few moments ago, we can just directly call by WebGL. We don't have to worry about vertex positions, which is great. So we will be getting to that pretty soon here. Let me just make sure I'm not... Okay, yeah. The next set of slides here is basically everything that I've already talked about. So why did we leave full screen? Basically, I'm going to skip through a lot of this, but this is effectively the code, and here's my lame Python joke. But yeah, this is exactly what I just talked about. So no difference, just we have this extra layer of indirection. Another thing we can do, though, is we can do index mapping. And this is going to be a slightly different take in that we are basically drawing, or we are tracking the indices that are going to form triangles. So we can, and this is just so that we're all clear on where we're at kind of mentally, since I'm just talking through the slides here without showing too much code. This would be a separate application, right? So this is not cube.js. This is a different one. I think it's like cube.v or one. I'll show you in a moment, basically. But instead of having color cube, we now have a list of triangle indices. And again, this is going to be the same notion. We have a list of vertices. Same thing, we know exactly where they're going to be. That's the geometry. We're defining the topology here. So triangle 1, 1, 0, 3. Do I have my cube? No, I've got to go back. So 1, 0, 3, 1, 0, 3. This is triangle 1. The next one would be 1, 3, 2. If we go back here, we should see, 3, 2, 1. Okay. 3, 2, 1. As long as we're going in the same order, that's what counts. But instead of building up vertices this way, we can build them up by face. Directly draw our triangles. This is going to lead towards that different WebGL call. And this is called rendering by elements. And what it's going to mean is that instead of passing raw vertex data, we're basically going to send the indices of our vertex buffer to the GPU instead of the raw positional data. A little bit different. You can use whichever you prefer. Performance-wise, not, as far as I'm aware, there's not a huge difference between them. It's whatever makes the most sense to you mentally. Now, how do we handle this? Well, we're going to create our buffer. Again, makes sense. This shouldn't look any different than what you're used to. It's an element array buffer, and we're going to push down the indices. So basically this list here. And instead of calling draw arrays, we're going to call draw elements. So still GL triangles, still however many vertices we have, still a byte, and then we have our extra parameter here. Not too much difference except we're calling draw elements. All right, so let's take a look at cube V now. All right, so don't get too excited about the coloring. Basically, it's just not mapping a solid face, that's all. And I love that the performance goes to hell when I'm streaming class, because normally this is not as bad as it looks. But same thing, nothing too different here, right? If we check the code, cube V, I've got you open somewhere. I want the HTML first. Guess I didn't open it. Okay. cubv.html. I should mention too, so this is doing that 3D spinning. Again, we're doing matrix multiplication to handle that. If we remember, like the rightmost position is applied first, we have to have that position there times our rotational matrices. Nothing has changed from the shader perspective. When we go into the actual application though, that's where the difference occurs. So we still have our axes of rotation. Again, this is just the cute little trickery for the demo. Make the cube spin, it looks pretty, let's rotate it on the axis. Okay, fine, no difference. Okay, we are still tracking the theta angle of each axis separately, and we're just toggling which one we're updating. No changes there. Differences though, from cube V to cube, we're still defining our vertices and our vertex colors in a list. The difference is where we are doing it. So in cube V, we're just going to define them as global variables, which, depends on how you want to represent things. If you want to be a little bit more better object-oriented programming about it, you could go that route. But still the same thing. We know where the vertices have to go. This is our geometry and how we style it. But now we're going to go ahead and, wow, I really need to start updating these spelling errors because they drive me nuts. These are not mine, by the way. I do know how to spell. But we can define our indices. So these are going to be the faces of our object, right? So here is that list that I showed you in the slide. What does our application look like? No change, no change, slight change. All right, so we have now this new iBuffer. So this is that extra line where we're basically tying our array indices into our list. All right, so we have that. We're also going to add on our color buffer. And we still need our vertex buffer in there. Okay, so we can't get away from this one, but we are adding on that extra layer of indirection. Render, it's going to look the same, except for draw elements instead of draw array. Now, what is happening here and why we can kind of get away with this, I'm kind of just zipping through this saying, yeah, it's not that hard, but it probably looks pretty complicated. All we're doing is saying, here's a list of indices. Later on, we still have our vertices, right? That's still there. All we're telling WebGL is by creating this buffer and saying element array buffer, again, this is different, element array instead of just raw array buffer, WebGL is going to parse out, okay, what are the indices we have to draw in what order? And then ship that off with draw elements instead of draw arrays. It's exact same object, just different coloring here. So in the slides, if you're kind of coming back to this later on, maybe you want to check because this didn't make sense or something like that. I start walking through adding rotation, updating render. Render here is the same, but we just use draw elements instead of draw arrays, and we would have this extra I buffer on it, or this extra, element array buffer set to I buffer. Okay, so what we've talked about so far. We are storing our vertices separate from our topology. So add an extra couple of data structures for yourself. Since we are in JavaScript land, we can just make use of lists. We can make use of how loosely typed everything is and just start tacking on parameters if we want them. It just depends on your needs. We can add on a different way of calling it. So we can use this draw elements feature instead of draw arrays. And we could go ahead and hopefully make your application life a little bit easier. That's really all we're getting at here. We want to minimize search time for vertices when we start deforming things. Questions so far? All right. If we are all good, I'll continue on. If you are looking through the slides, I've got some in-class assignments. We're not necessarily going to step through them today anyway, because I kind of want to move on towards Blender. But what you could do if you want some practice with this is you could take cube.js and cube.html and turn them into a draw elements function. All right, since we only have like basically 15 minutes left, this is going to take a little bit long, I would think, for that. Plus, I can't really help you too much on stream. But if you want to try this out, feel free to go for it. Basically, what you would do, take cube.js, take cube.html, update the shader, which we don't have any updates to make, and then get rid of that color cube call. And what you're going to want to do is instead of call color cube, initialize the vertices, initialize the vertex colors. And this is going to be cube v if you want to look at the working example. So basically you're going to want that list of indices. You're going to want the list of colors that goes with this, and again, check out cube v. Instead of flattening colors and points, flatten vertex colors, flatten vertices, add that extra buffer to handle the indices, and then use draw elements. So that would be your basic way of taking a draw arrays function and moving it to elements. Basically, you just need to track the indices. It's kind of the TL didn't listen, TLDL, I guess. So we have that. And if you want to go a little bit crazier, scale it, translate it, and see how that plays out in the shader. Again, you did this in one of the most recent labs, scaling and translating and all that fun stuff. Pretty sure you did it recently. You don't have to show me because I'm not going to make this an in-class assignment, but kind of a nice way to start playing with shaders and understanding how it goes. Yeah, don't worry about this part. And this little bold point, for some reason, my last group of students decided to save their web pages as .urls and then send that to me. But we're not going to get to that. Okay, I guess I should triple check. No questions, right? We're all good with that? Otherwise, we'll start talking perspective and then we'll end there. I guess T Sweezy, did I answer your question from like a half hour ago? Make sure I got that. Awesome, okay. I realized I never followed up with you. All right, so keep in mind that what we did there was for WebGL because we can take advantage of draw elements if we want. That's going to hold in Unity and any other language. It's just going to be already there for you. So when you're going to plop an object into the Unity engine, like you drop it onto the canvas, or you drop a, you have the default Blender cube there, that thing is already abstracted enough, right? You can go into the Unity properties bar and tweak its position, tweak its scale, do all that stuff that we're doing with raw matrices in here. They have all of those extra layers of indirection already built in there for you. It's just here you have to manage it yourself. All right, so we're not quite at day the second yet. I wasn't sure if we'd get through that or not, but I'm kind of glad we did. Let's start talking about some perspective. So the way this part is going to work is that we're going to talk about the different ways to look at things, and then we're going to figure out how we can use our camera to do that. Again, our cameras in WebGL. Sorry, one sec. Can I help you? Okay, thank you. Guys, I'm in class right now, okay? I'll be up in a moment. Hi. Yep. I looked down and there was a hand under my door. It was kind of creepy. It's like if you have a cat sticking its hand under the door trying to paw around. Except as a kid. All right. So, we'll get to that. Okay. So let's get some perspective. And since we have this nice, pretty perspective drawing of a house, we've got to bring in our classic music video from Aha, which is delightful. This figure here is from way back when we talked about the pipeline, right? Except we're starting with our vertex data. And we started talking about the different types of matrices and how they're going to be transformed along the way, right? We're going to build up that current transformation matrix as we go from point to point to point, and that's going to change how things are represented. So we start off with our raw vertex data. That's what you push down onto your buffer. That gets sent to your shader, and then you can play around with these matrices. Actually, I should step back a little bit because what we're going to be doing in here is we're going to use some of the library function calls to actually build up some of these matrices and then send it to the shader. So I jumped ahead a little bit there. But we have our vertex data. This will basically populate a model view matrix, which if you break that word apart, it's going to be what your model is represented as plus the view. So we're going to get 2 for the price of 1 here. That's the object coordinates going in. Coming out, we're getting our I coordinates. So basically, how are we looking at this thing? What is the view? After that, it's going to get transformed to a projection matrix, meaning what is the exact way we are looking at this thing? So kind of this aspect here is what we're talking about with perspective. After it comes out of projection, we're going into the clip coordinates, meaning that we're trimming off everything that we don't need. We're going to normalize things with our divider, right? Remember our homogeneous coordinate divisor. and then we're going to translate it down to a 2D image into our window coordinates, basically. Kind of the key thing to keep in mind with all of these steps, we are doing our darndest to stay in 4D space as long as possible. So basically everything's going to be a 4x4 matrix all the way up until the very end. And the reason why we do that is so that we can keep as much information as possible until the last possible moment. Once we start applying transforms, once we start clipping, we start losing data, right? Because things are no longer shown. Or we translate from a 4x4 matrix into a 2D set of pixels. We lose information at that point. But earlier on, we know things like depth. We know things like perspective. Once you get here, this is just raw data for the display to show. So let's talk about views. And this was the only thing I could find on high level for Google Images. Some little town in Alberta with a cash store. So, anybody ever do CAD or drafting or anything with technical drawing before in here? I did it in high school. We did AutoCAD and we did drafting by hand and all that fun stuff. I thought it was a blast in high school. That's when I did it too. Took a high school CAD. Hey, awesome. I'm glad I'm not the only one. I thought that was so much fun. Our teacher was interesting, to say the least, but I think that's any high school teacher. One of the most fun things we did in that class, which I was awful at because I am not an artist. You all see my artwork. We did is the aerosol spray. Like you get the little spray, like the little motor and the spray thing, and you can do shading on actual drawings. It was a lot of fun, but I was awful at it. Anyway, it was also in the days when AutoCAD was on a green screen, was what we used. But what do we need to actually view something? So those of you that did CAD, I guess, will probably be yanked back to high school for some of this. So to look at things, we need objects to look at. We need a viewer, and we need a projection surface. And what basically this means is that, you know, any 3D object, let me grab Link here because he's going to be helpful for me. I swear I haven't started losing my mind, by the way. No, you haven't started losing your mind. This is very clearly a 3D object in my hand, right? He has a front, he has a back, he has properties, so he's very squishy. I can deform him, I can do whatever I want. But to you, he is a 2D object. Okay? So by notion of the camera that I have here and the technology from translating camera images to a 2D screen, Link is being projected from a 3D object to a 2D plane. Okay? If I do, you know, I have him sit here and I kind of angle him this way. Let's try to do a angle this way. Don't show off your backside, Link. Kind of an isometric view, hopefully. So Link is going down his isometric viewplane. Or he's top down. You know, we're doing Zelda 1. Or he's kind of could see his face, right? Basically, we are taking our camera, and our camera is going to be a pretend object. You know, we are dealing with it kind of here. We're just transforming how the pixels are represented. So, with that, we're going to get into some terminology which kind of stems from classical arts, from viewing, from CAD. All of these notions play in here, and we're going to take all these ideas and we're just going to plop them into some function calls, which is going to make life easy for us. So if you want your camera to move, we're going to call the look at function, you know, look up here. We're going to tell it maybe which direction is up, depending on which function we call. But we have to know all of these kind of terms because what are we doing? We're building a 4D matrix based on if you want perspective, if you want isometric, if you want oblique. Basically, we're just building up matrices and filling in slots for that. So the reason why we have these different views, though, is that we can get different information from them. So those of you, and I'm not trying to like cut out the people in class who have not taken a CAD class, but we have different perspectives to show different information. So if you're trying to do an architecture drawing, it's not going to be photorealistic. You're going to get angles that are wildly out of place, but maybe the length of lines are preserved. But what you're able to do is you can show multiple faces of an object while still kind of retaining what it should look like. It's going to look distorted, but maybe the architect can see three faces instead of just one. And it's not going to be perfect, but we can build from that, and we know how to get from that view to the real object. So, what is a projection? We are going to take an object and project it onto a 2D plane of some kind. And if it's already a 2D object, nothing hard that we have to do. We have X and Y. If we have a 3D object, we basically have to orient it in such a way that the exact lines that we can draw, say, from that object make sense on this 2D plane. So we have these notions of projectors where either they converge. So our view here, my camera would be like the point of convergence, and think of like lines coming out of it. And what this kind of gets us is that if I put Link right here, he's super close to you. As I pull him farther back, he gets farther away. And yeah, intuitively that makes sense. You know, what are you talking about, crazy old man on the camera? If we have a parallel projection view and I do this, he's going to look the exact same size. That's kind of the takeaway. Based on which perspective we use, we can get different information. If you're building a video game, you just pick a view and you go with it because that's the style of your game, right? I want isometric. I want third person. I want first person. I want over the shoulder, you know, Resident Evil style gameplay. Fine. Pick your perspective and go with it. But if you're doing a graphics application for, say, a simulation or an architectural diagram builder, right? If you're building the next Google SketchUp, these projections can and will change, and you have to build up a matrix to handle them. So with this, we have this notion that based on our projection that we pick, maybe we preserve lines, not angles. That would be where things are slightly distorted, but we can see more. Or we can do a non-planar projection, where you get something kind of like this. So kind of like your fisheye camera lens in a way, where this is very clearly a 2D object, but this doesn't look like a real picture that anybody would see. Or like if you were standing in the city, it wouldn't look like this, right? But we get more detail, we get more information in a smaller amount of space. So think of like your map projections you probably heard of, right? If you look at the standard 2D map of the globe, that's not what the world actually looks like, right? It's been projected so that we can make sense of it. And if you don't know what I'm talking about, look up map projection in Google Images because you can see some interesting things. And there's also a lot of very angry map makers out there too who talk about it. But here are some of our classical projections, and let's see, we'll probably end right around here somewhere. So this are going to be some of your like things you'd probably see in a CAD class or an art class or something like that. Basically, here's some of our different views of objects. You have your front elevation. You have oblique elevation, planned oblique, 3-point perspective, 1-point perspective, isometric. Again, whether you took CAD, whether you've ever played a video game before, or you just know this stuff, you probably have heard of some of these angles and some of these projections. When I talked a few moments ago about angles not being preserved, so these are all the exact same object. Okay, so we have kind of a, you know, like a Roman or a Greek temple going on here, a Parthenon-esque type of object. This is all the exact same thing, but we see different information based on how we look at it. So here, elevation oblique. Look very carefully at this corner here. Right? If I were to, you know, try to build this Roman temple or what again, whatever it is, this angle, if I just looked at this figure, would be greater than 90 degrees, right? So it's kind of um, like 135 or whatever that's going to be. I'm not sure what the exact angle would be. In reality, this is a 90-degree angle. This is a square corner. But it doesn't look square because it's an oblique view. Here, 1-point perspective, these look like they're acute angles, right? So this is probably a little bit over 45 would be my guess. This is still a square 90-degree angle, just based on how we're putting our camera and based on some mathematical trickery, we're showing different information. What's the benefit of something that looks horribly distorted like this? Well, I can see the entirety of this face. I can see the entirety of this face. I could, if we're doing an architecture or a CAD type application, here's the exact length of this set of lines. Here's the exact length of these lines, and I can put everything on one figure. Or if I go isometric, our angles are a little bit more preserved here, but we don't get to see anything in the back because it's hidden. Here, we can actually kind of see these pillars there. Or 3-point perspective, we actually can see pretty much the entire object, but things are going to be slightly distorted again. Yeah, if you did a high school CAD class, you probably did the isometric more or less. So you'd have like the front, the right, and the top view, and then in the top left corner would be your isometric view, putting everything together. And you probably looked at some of the other ones too. But what are we getting at with all of these things? I'm going to mention this again next time. We don't care what the projection is. Okay, that's a bad thing to say. We care, but this is all going to be the same for WebGL. It's just a 4x4 matrix that we're filling in differently. If we're doing an elevation oblique angle, we're going to have some cotangents in there. If we're doing isometric, we're going to have some different offsets in there. Basically, it's just filling in the blanks in our matrix. And again, that's going to be how we populate that current transformation matrix as it moves down the pipe. All right, we will end here with this slide. I just want to kind of give you the categories of projections that we'll be dealing with here. So we have this entire field of planar projections, and all that means is we're taking an object and displaying it on a 2D screen, which is exactly what you're going to be doing with graphics. Do you want a parallel view or a perspective view? All right, a parallel view means that we're going to have parallel lines kind of going off into space. And based on how we orient them, we get different views. If you remember nothing other than one notion from here, your isometric view is going to be parallel. Okay, that's kind of how I remember, because we have all these other views which we very rarely use in games other than like an isometric perspective. If you want that kind of, angled XY movement in your game or your graphics. Perspective views are different, and this is going to be based on how many faces we can really see. So do you want a 1-point, 2-point, or 3-point? If we look at this guy, this is a 1-point projection. 3-point, we see a lot more. Sorry, this is the 1-point. It kind of gets into vanishing points and things like that. Basically, how many lines do we have going off into the distance? We'll get to that next time. But if so this is going to be what I mean by projection, kind of. So let's take our little figure here. Let's move it around in space, move our camera around. Based on how we've oriented things, that's what shows up on our screen. And that's what we're going to be getting to. Alrighty, right on the dot for 5:14. So any questions left over from today? I know, Chris, you wanted to chat about the lab, so we could chat on Discord about that if you'd like. But we end here. Yep, okay. Anybody else have any questions? Otherwise, we'll just drop the stream now. So, all good? Good, good, good. Hope you all have a wonderful day. I will see you all on Thursday. Ended here. Exclamation point. All right. Okay. Bye, everybody.